You guys pulled up? Pretty sure. No, you were just there just before your foreign language.
Latin is.
Yeah, like I said, I'm pretty sure those are part of your courses like this, so you can't get out of it. Well, you can, but you have to.
Recommended but not required.
Yeah.
Okay, that's.
You can get out of it by going to a different university. So to be honest, pretty much every university now requires a foreign language at least for 2 semesters.
Okay.
That's not
Yeah, I'll do Latin or French.
a little bit of habla español and you're going to right?
I don't habla español, but I do parla francés.
There you go. So if you want to go work international, that's useful to make for the UN.
Yeah.
And the atomic energy.
Yeah, because France is. Are they still believe that they're part of China?
No, China's not.
Wait, no, I am not
France
lying.
is paring back.
Really?
Yeah.
I mean,
Same reason everyone has regulations and public opinion. So.
yeah, but I mean, they power not just themselves, but other countries as well.
No, I'm not arguing against it. I'm just, I'm just saying that's what it is. Alrighty, so here we are. We're deep into the semester now, having gotten 1 day already of general chemistry. And looks like you guys are starting to get a little bit tired already, right? So time for another break, and it's all good. So last time we just kind of sat there and chatted a little bit about the intermolecular forces, and I tried to bring back in some of these topics that we talked about in Gen Chem 1 there, about how they relate to the intermolecular forces, and just to kind of knock the rust off, so to speak. And we remember things like orbitals and where the electrons are. We talked about the periodic trends with electronegativity and a little bit about radius and all these kind of things that kind of go together in there, right? And that's all useful, I guess, to describe our intermolecular forces, which is one of these topics which we'll see. Let me think how do I want to put this. We'll see it kind of come up here and there throughout this semester. But it's not like something that I'm really going to point back to, just because, kind of like what I mentioned, the second semester of Gen Chem focuses more on, I would guess, the quantitative side of things. And so what I mean by that, or maybe, I don't know if it's a useful story or not, but when I was taking Gen Chem 1 and 2, we didn't call it Gen Chem 1 and 2 because that would make it logical, right? We called it qualitative chemistry and quantitative chemistry is what it was. And so if you think back, and we had a couple of chapters in Gen Chem 1 where we did, kind of heavy math focused enthalpy and the gas laws and that kind of stuff. But the rest of it was kind of just like describing, how reactions happen, that kind of thing. And so I just kind of emphasize this again because of the big sticking point in Gen Chem 2 is just the, being able to do word problems, right? Being able to extract the data out of the information in a problem and then putting that together into a coherent equation to get the answer that you need, right? We have the dreaded M word that comes back over and over and over again, right? So I'm just getting you guys prepared for it. Just, it's going to be there, very math heavy, all that kind of stuff, right? So nothing to be afraid of, just something to be aware of, so that you guys, start working through that now and kind of, get comfortable with using the equations that will come up, right? But anyway, what we'll do today is we're going to kind of go through a little bit more and kind of talk about some of the other maybe refresher things from Gen Chem 1, and then after we're done with this kind of section, then we'll really get into some of the new stuff too. All right. So I think it's an announcement. For some reason, I just can't. My recorded lecture for OChem worked fine. I don't know what happening here. So I gotta. It's always something, I swear. But I'll get that out for you guys as soon as I can. I promise. So it'll be there, so you guys won't miss anything. The good news is, and I've always said this, and I've always kind of mentioned this as a point, I guess, for any class that I teach. So you guys are in general chemistry, and that means you guys are one of thousands of students taking Gen Chem mean with, not here, of course, right? But what I mean with that is there are so many resources available online for you guys, right? So, I know this isn't the case, but in a hypothetical world, right? You're like, it's an 8 a.m. class, he's got an annoying voice, right? I don't really want to go listen to him. I'm going to stay home. Fine, knock yourself out, right? So, but make sure you guys are keeping up with some kind of lectures somewhere, right? There's plenty of universities out there that post their complete lectures online. And joking aside, I know I don't speak to everybody in here, right? Some of you guys listen to me and like, he's fantastic, right? And the other 29 of you are like, right? No, what I mean is everyone's going to learn a little bit differently, right? Everyone's going to present this material a little bit different way. Right, so if you're having trouble understanding what I'm saying, and you come to my office hours and it still doesn't make sense, and you read the book, and you go to tutoring, and you watch the Khan Academy, if you do all that and it still doesn't quite click, then there's plenty of other lectures that are recorded online there too, right? So just there's no excuse not to get the information that you need, right? I want all of you guys to be successful in here. You know what makes my job easy? When you guys all get hundreds on everything, right? Why? Because then when I'm grades, I'm like, oh yeah, easy, 100, right? That's easy. I don't have to sit there and, okay, how much partial credit? Well, okay, they just swapped the minus sign, so that's a -1. Well, they did 2 minus signs, so that's -1.5. And then I have to get out my calculator because now there's half points, right? That takes time. Just get 100, get everything right, okay? And then life will be easy for me. And I'm happy, and you're happy, right? And that's what we want, right? One person agrees. Thank you. The rest of you guys are like, no, I'm not going to do that. I'm going to make life miserable. I'm going to miss things on purpose. Right? But anyway, so the point being, all of you guys are capable of getting an A. I promise that. I promise that. Some of you guys, it's going to be a little bit more difficult to do. Okay? Because chemistry is not your thing. And maybe you're not as comfortable with math as somebody else. Okay? But all of you guys are capable of doing that. I promise. Okay? But it's going to take a little bit of work for some of you guys, and for others, it's going to be a breeze, right? That's just the way the world is, right? Everyone's a little bit better at certain things. All right. Anyway, I think that's all I kind of needed to share with you guys. Oh, did we ever find out? I think there was some confusion. I didn't look at it either. Was there a lab for you guys this week or not?
There was an intro labby thingy, but it was watching your beautiful safety video with the Beatles bowl cut picture.
Yeah. I should monetize that so I get up to like 3 cents a year off of it. So requiring you guys to watch. No, I'm just kidding. Okay, but yeah, make sure you guys are keeping track of the lab stuff too, right? Lab is gets factored into your grade here, right? So that's a great way to kind of basically boost your grade in here also, right? It's online, with the stuff that you guys submit there, and just show up. And if you have questions, Dr. Tong is around and Dr. Freeze are around. They're fantastic. If you guys need help with the lab stuff too, right? And I'm sure Laura, the tutor, can help you guys with the lab stuff also. I think there's some new labs for you guys this year too, so I'm waiting to hear what happens with those, but we'll see. All right. Anything else then before we launch into it? All right. Cool. So I will probably not this week, just because there's still a drop ad and that kind of stuff. But next week we'll definitely I'll put up a couple of problems that we'll put together into an assignment that we'll call a quiz for you guys. So just be aware of that. That should pop up on Canvas for you guys, and there'll be a couple hours for you guys to get it done. Right?
So it's going to be open book stuff again?
It depends. It'll just depend on what it is. Maybe for some of them yes, for some of them no. We'll just, I'll give you guys the instructions in there. Cool. All right. Well, before we launch back into it, we'll start with some prayer, and then we'll continue on here. But Lord, we just thank you for another day. We just thank you for another opportunity, Lord, just to gather together. We thank you, Lord, that we have this beautiful day that you've created for us, Lord. And we just pray to be good stewards of the time that you've given us, Lord. Just help us to use our talents, our gifts, and the things that you've given us, Lord, just to share your word with somebody else, Lord. Just give us an encouraging word for somebody today, Lord. Just help us to see somebody who you want us to share your word with, Lord. And just put that on our heart and give us the strength and the courage to step forward, Lord. We pray all this in your name. Amen. All right. So, we have finished talking about the intermolecular forces, and now we kind of talk about some different states of matter here. Right? I know this was, these slides are, I think, the exact copies of what I did back in chapter 1 of Gen Chem. Right, so I'm gonna kind of go through these pretty quick because there's nothing necessarily new about them here, but we've talked quite a bit about solutions in the first semester, and we're gonna talk a lot more about them this semester also. We're gonna learn a little bit more about solubility and how we can actually calculate how soluble things are, and we're also gonna talk about equilibrium and these kind of ideas that come along with it there, right? So I don't need to talk to you guys too much about this slide right here. You guys are more than capable of reading it on your own, right? But some things that we can maybe come back now and take a look at is, we mentioned viscosity very briefly in the first semester there, right? It's just, you know, a measure of flow, right? And it's how well do the molecules flow over each other. Now, if you think about this, right, it's kind of a, maybe the best analogy is when you kind of slide your hands back and forth, right? There's a motion of one hand over the other one here. And we know that there's a certain friction that has to be overcome and all these kind of things with it, right? But of course, friction isn't really something that we have to care about when we're dealing with the motion of molecules. But the idea is there's some stuff that's holding these molecules in place. And those are your intermolecular forces, right? So remember, it doesn't matter if you're in a solid, liquid, or a gas. The intermolecular forces are the intermolecular forces. Those are just the way that molecules talk to each other, okay? The closer those molecules are, right, just like in a liquid, right, they're fairly close to each other, the more they can talk, the better that communication is, okay? And so if you think about what the energy takes to make something flow, right, if I take my cup of coffee here and I poured it out, right, there's an energy that would be required for those water molecules to flow over each other, okay? And that's basically a measure of the intermolecular forces. In fact, there's some experiments that if we taught physical chemistry, which is one of these upper division chemistry classes, right, there's actually experiments you can do to measure that energy of activation to make things start to flow, right? It's a pretty simple experiment actually for something that gives very complex information. Right, but that's all we can really talk about there with viscosity, right? It's just kind of a visual representation, in a way, of the intermolecular forces, right? If something like honey has a high viscosity, right, that probably means that the molecules that comprise honey are talking to each other fairly well, right? So it takes energy for them to flow over each other. Okay? And honey is basically sugar. And what is sugar? Well, stuff that has a lot of hydrogen bonding, right? Okay, so here's just a kind of this and that, higher viscosity, lower temperature, blah, blah, blah. I'm not gonna, like I said, I have no interest in verbatim reading slides to you guys. You guys have access to my slides online, yes?
Yep.
Everybody got them? Cool. And so you guys can read through this stuff on your own. Large entanglement of molecules, wow. Of course it is. Anyway, right? But anyway, so just stuff to start to think about here. Now, why I want to put this back is because we're going to talk about surface tension. And so surface tension is kind of a similar idea to what's going on here. Now, I don't think we talked about this in the first semester at all, right? But you guys have probably seen, there's a bug can walk along the water, that kind of thing. And why would that be, right? Well, maybe the best visual representation is kind of going on here, right? So if we have these individual molecules kind of floating around in a container, right? The molecules on the surface are going to have a different amount of force, or are going to feel a different amount of force than the things that are in the middle of that, okay? And so that's all I'm talking about here, right? The stuff on the surface there has a net downward pull, right? And that creates the tension, where the stuff in the middle has an equal pull from everything around it, right? So remember, we have to kind of think of things in three-dimensional space here, right? So anything that's in the middle here kind of has an equal attraction to everything else around it, so there's no net pull. Or on the surface, it's a little bit different, right? But what do we mean by a net pull? How are these things talking to each other? Well, yeah, there's three ways, right? Your intermolecular forces. So again, all these things are at play here. That's all we really want to talk about. Okay?
Hey Doc, the
Yep.
slides appear to be slightly different. Yeah, like that.
You're
one.
missing some, or I'm missing some.
No, we are, cause that's.
Oh, that's not my problem then. I'm just kidding. Okay, I'll go double check. Maybe I accidentally put the wrong versions up there for you guys.
Yeah.
Oh, okay, yeah, I'll go fix that for you guys. Sorry about that. Yeah, maybe I just put the older version on there for you guys. You guys want pictures of bugs? I got it. All right.
Bugs are great.
Right. Cool. Anyway, so more examples here of just the intermolecular forces and how they work. Right? And we could go through and we could talk about, the different surface tension. You can actually measure it, right? And there's certain experiments you can do with that. And that's a little bit more of the physics based with that, right? But the definition that we kind of give there, right? Surface tension is equal to the energy required to form a flat surface. So there's a certain amount of energy that has to be overcome to flatten things out, I guess might be the way of thinking about that. Right, but different, what's up?
Maybe I'm totally missing this. Does this mean that you can like blow mercury like glass?
What?
Does that mean that you can blow mercury like you blow glass?
No. I don't think so. Right, I mean, mercury is a liquid, right?
Yeah, why is glass in the center then? Like,
It's just an example of differing, the different forces that we see, right? That's all.
so mercury.
Is this liquid glass?
Yeah, that's why I said it's just like glass at a high temperature, right? It just has different stuff, right? Just everything is a liquid.
So acetone has the least surface tension and mercury has the most?
Right. It takes less energy for acetone to kind of stick together is what it is, right? And so it'll just spread out. It won't puddle up like, form a droplet like mercury will.
Okay, gotcha.
Yeah. Anyway, so the question, then the common question that might come out of this is, why do raindrops form, right? And there's an argument of intermolecular forces there, right? Does the water want to interact with the air molecules, or would they rather interact with themselves, right? And we'll come in just a second about this, or a slide here in just a minute, about osmosis, right? How does water travel up from the roots of a plant all the way to the top, right? These kind of things. And so it just takes a certain amount of energy to form a sphere. It takes a certain amount of energy to make that sphere kind of spread out into a puddle, like with the acetone there is all this. And that energy has to come from somewhere, right? And so that's the other end of this. And if you remember in chapter 5 of Gen Chem, right, we talked about energy of a system and the energy of a surrounding, right? And we talked about the measure of a certain type of energy, which we called enthalpy, right? Delta H, you guys remember that?
Mm-hmm.
3 of you guys do, okay, the rest of you guys again right now.
The magic styrofoam cups.
There you go, that's right, the highly scientific styrofoam cup experiment, right? Which I think you guys will use those again this semester.
Oh boy.
Are you guys doing one of those experiments where you have to measure the enthalpy of fusion for ice?
No idea.
That's usually like the first experiment you guys do. So you get to play with ice and water.
Oh,
and a thermometer.
Oh boy, whoa.
But anyway, so like I said, I don't need to keep reinforcing this stuff for you guys here, but just all the idea that we have here is that these intermolecular forces are all going to be kind of working together for different properties. Now, this is something you guys probably talked about in biology at this point, right? How does water get from the root all the way to the top? There's a cool little, these glass demos that we see here. The smaller the diameter of the tube there, the higher the water can climb. Well, why would that be, right? Why would that be there? And then you can turn. I think I actually did this one time because that's what my life is. You can change celery different colors. I don't know. It looks cool, right?
Yeah, my mom tried to do that with carnations once. It didn't work.
It didn't work.
No,
Interesting.
they were already dead.
Oh, science. All right. So we can talk about adhesion and cohesion and all these kind of things. For those of you guys who haven't had me before in a previous class, what you'll know is I'm never going to say, give me the exact definition of cohesion as it is in the book, right? It's just not a good question to ask, right? I might be asking you guys to explain cohesion and adhesion and surface tension and these kind of things. And ask you guys to come back with some kind of explanation about the intermolecular forces and that kind of thing, right? I don't need you guys to memorize definitions. Why?
Because you want us to understand, not memorize?
That's true, right? But all of you guys have this thing called a phone, and your phone has Google, and can Google give you the definition for something? Sure, but can Google help you to understand something? Yeah, right, but when does the understanding really happen? When it's what? Not Google's words, but your own words, right? So there it is. And the older I get, the less relevant this slide always becomes. Just because you know, mercury thermometers used to be kind of a standard. Right now, nobody uses it anymore, right? Which is a shame, because every time we had a broken mercury thermometer, it was always kind of fun to, you know, play, you know, find the mercury and play with it. But then mercury, you know, mercury gives off some vapors, and you don't want to be breathing that in, and so all the fun things in life get ruined, right? So, but I believe the first lab that you guys had for Gen Chem 1, you guys learned how to read volumetric flasks, right? And you guys had to read the meniscus and all these kind of things, and Dr. Tong is very strict on his significant figures. Right? How's Dr. Freeze with sig figs? Is he a little bit? He's a little bit lenient. All right, okay.
He's taking cues from Dr. Tong.
He is. Oh, I feel sorry for you guys. I'm sorry. Luckily, I don't. Well, I would say you guys. I don't care about sig figs in here, at least, right? So I think part of the challenge already is just understanding and getting the math right. I don't need you guys to stress too much about the sig figs. If you guys want to go for it, knock yourself out, right? I'm not gonna. It's not like I'm gonna take off points. But just do me the favor of, if you're doing a calculation, I don't need 10 decimal places. Okay, it's a little bit overkill. So just keep it in check, I guess is all it is. But anyway, so why do we have these different meniscus? I don't know. That's a good question. Right? Why? I don't know what's the plural of that. But anyway, so why do we see these different forms of a meniscus for these two different compounds here, right?
Surface tension?
Yeah, that's part of it, and also the difference coming from, you know, the water interacting with the side with the glass versus the mercury interacting with the glass, right?
So the water has higher adhesion?
Yeah, so glass is polar, right? We've got silicon, we've got oxygen, there's a big difference in the electronegativity, right? The water can start to form hydrogen bonds with the glass, and it can kind of basically crawl up the sides there is what it is, right? But mercury doesn't really have that ability, and so it just kind of would rather stick to itself rather than stick to the side of the glass. Okay? So that's all it is. All right. So a little bit about vapor pressure. We started to talk about this again in the gas laws chapter. You guys remember when we mentioned the idea of collecting a gas over water, and we talked about partial pressures. Does that sound familiar?
Yes.
Yes,
I don't remember how it works, but it sounds familiar.
Okay, well, partial pressures is pretty easy, right? So, what's the pressure that you guys are feeling in this room? Well, my parents expect me to do good, right? I need to keep my grade down, right? What kind of pressure are you guys feeling in here?
Air pressure.
Air pressure, right? About 1 atmosphere of pressure. Why? Where's that pressure coming from?
The atmosphere.
Well, the air that's around you, right? You're basically sitting under a giant column of air right above you, right? And that's the weight that you guys kind of feel there, right? So now, is air a single component? Well, no, of course not, right? It's got nitrogen, right? We've got oxygen in there, we've got carbon dioxide, we've got some water, we've got, you know, a little bit of a couple of other, you know, smaller quantities of gases in there, right? And each of those individual quantities exert a pressure, right? So if I gave you guys a volume, right, and I said there's a mixture of those gases in that volume, you guys could calculate the individual pressures, right? Because PV equals nRT, right? And if I ask you to calculate the pressure of oxygen in this room, right, you guys could get an answer. And then calculate the pressure of nitrogen in this room, you would get an answer. Right, and the pressure of CO2 and all these things. And if you add up those individual pressures, what should you get?
1 atmosphere.
1 atmosphere, right? The total pressure that's in here, right? That's what the partial pressures are, right? The contribution from the individual components in there. That's all it is, okay? And so we talked a little about vapor pressure with that when we collect a gas over water, which is actually a very common way that we measure gases that are created in the lab when we're doing an experiment. Did you guys do the experiment where you collect oxygen and burn different things? Was that you guys, or was that the nursing chem class? I forget.
Probably nursing.
You guys didn't get to do fun stuff like setting things on fire?
We did get to do one open flame experiment. I was banned from open flame experiments.
That makes sense. I'd agree with that.
But there was this thing, the copper and the flame.
So you guys were burning the different metals and it came out,
Yeah.
So the spectroscopy stuff, and you guys
Yeah.
were looking at the different ways, yeah. So there is an experiment that we do, I believe that it's in the elementary chemistry class there, where you can actually collect oxygen, you can burn different things. I would have to be careful. You guys could actually do it at home, although don't. Right? I have to be very careful. Like, well, you encourage me to set things on fire at home. I don't know, that's not what I'm doing. I'm just saying there's common ways that there's some of these common experiments that you guys can look up online, and that's actually kind of neat. We are unfortunately restricted with some of the experiments we can use because of safety concerns here. But if you're bored on a weekend, I can't stop you from doing anything, right?
Go out into the swamp and do the thermite experiment.
And you gotta scare the alligators in, right? But anyway, so vapor pressure again is just the measure of the pressure exerted by an individual liquid or any kind of material, right? Technically, everything has a vapor pressure to it, right? You're like, well, what about the desk that's in front of me? Well, some things, maybe if you want to think about it, some things take a really long time to evaporate. For instance, okay, you guys all know that if you have a beaker of water or something, you leave it out, it's going to take some time, but eventually it'll evaporate, right? If it's not at the boiling point, how does that happen, right? Why does a beaker of water at room temperature eventually evaporate? Well, we'll talk about that a little bit later in the semester as to why that is. Okay? But for instance, what's up?
Isn't it something to do with like the temperature of the air means that it can hold a certain amount of water and humidity, so the higher the temperature of the air, the higher level of humidity, and if the actual humidity is lower than what the temperature can like allow, then the water goes. I'm great at this.
So what you're hitting on here is something, I guess we could think of that as equilibrium, right? And we'll get into that in a chapter also, right? But and while it sounds like it's all correct what you're saying there, and that doesn't quite answer the question as to why do things evaporate, right? Because what evaporation is turning from a liquid into a gas, which happens at the boiling point, right?
Because there's not enough pressure to hold water in a completely liquid form.
Maybe, but there's another, so we'll get to that in just a second, right? So, anyway, vapor pressure will be, it's just kind of a measure from the individual components in there, I guess. And where is it? Here it is. So maybe this is a good statement to kind of keep in your back pocket there, the one in the middle. So when does something actually boil then? So the mathematical definition of boiling is when the vapor pressure is equal to the atmospheric pressure, okay? So it really isn't so much dependent on the temperature, right? Although vapor pressure changes as we add energy into a system, right? And that's why we have to take water up to 100 degrees Celsius, so that the vapor pressure of water at that temperature is equal to the atmospheric pressure, and then it starts to boil, right? For those of you guys who watch sci-fi movies, right, and you're out in space, and what happened, they always say that as soon as you get ejected out into space, right, your blood boils and all this kind of stuff, right? All these kind of scary things happen. So we'll stay away from maybe the kind of the morbid question here, but what would happen if you put a mug full of coffee out into the emptiness of space? Well, it would start to boil, right? Why?
Because there's no pressure.
Yeah, there's basically no atmospheric pressure out in space, right? So the vapor pressure of the liquid is much higher than the atmospheric pressure. It would just start to boil away, is what it is, right?
What if
So-
you threw a squirrel out of an airlock?
Well, look, that sounds like one of these proposals to send to the National Science Foundation, although you're gonna have some ethical concerns with that. So, but anyway, what was I gonna say now? Distracted me with your squirrel question.
If it
Oh.
makes you feel better, I ask a lot of squirrel questions in calculus too. Like on Monday, I asked about
That doesn't make me feel better. But anyway, so what we can say is we can change the boiling point of something by changing the pressure, right? That's where I'm sitting my coffee. I'm kidding, I'm joking.
Yeah,
So-
I'm fine.
So if you, any of you guys in here from, Denver, maybe, or Colorado? Higher elevations than Florida, I guess everybody is, right? You know, because what's the elevation here, like 7, right?
Here,
Right?
I would just.
Yeah, it's like 20 something, yeah, but anyway, if you take a look at the back of like certain boxes of food, it gives you the instructions on how to make it, right? So you open up your instant rice and you throw away the box and you forget you didn't read the instructions, so you have to go root through the trash for the box, right? And on the back it says standard preparation, right? Here's how much water you add and put all that stuff in there. And in some cases they say at higher elevations, right, you have to change the temperature and change how much water you add into there, right? I've seen this mostly on like the pre-made brownie boxes, right?
Cake.
So, yeah, cakes and all that kind of stuff, right? Because when you're at a higher elevation, the pressure is decreased, right? So water boils at a lower temperature when you're up in, you know, Denver than it does down here, right? Because they have less pressure up there. And that brings in, you know, certain adjustments that have to be made with cooking, so to speak, right? Among other things. Alright. So just here's kind of a visualization. We'll take that exact same idea that I just gave there, but kind of put it into a graphical form, right? Lowering pressure, right, lowers the boiling point and all these kind of things there, right? That's all this is showing you guys, okay? Now, something important to maybe recognize is up there at the top. I think there's a question coming up here that you'll need to know that, right? So we're at 1 atmosphere and there's 760 millimeters of mercury, this kind of stuff, you know. So just kind of good to know that standard temperature and pressure, which we talked about, and what's the pressure, you know, in here at sea level, that kind of stuff. Right?
Torrs are equal to mmHg, right? Or
Is it? I think that's what it is. Honestly, I always have to look those up. Yeah, there's so many different ones, and I don't have enough
it just
room in my
exists to
brain.
confuse us.
Yeah. Yeah, there's different reasons for it, right? But some of it does come down to just this is what they traditionally use to measure things with, right? Anyway, so down here, right, just kind of bringing back a little bit of terminology here from things that we talked about. When you take a liquid into a gas, right, we can measure the energy that's required to do that. That's the heat of vaporization, right? So we talked a little bit about that when we, in the enthalpy chapter again, right, we talked about the enthalpy of vaporization, right? And when we go from a gas back into a liquid, right, that's the heat of condensation, right, the enthalpy of condensation there. Now, what do we know, or what's the relationship between the heat of vaporization and the heat of condensation?
Equal.
Not necessarily equal, but if it takes 100 joules of energy to vaporize something, what happens when you condense it?
It
You release, right? You release that 100 joules of energy, right? So in terms of magnitude, they're equal, right? It's 100 for both of them, but the signs are going to be opposite, right? So it says condensation is exothermic. Now I know you guys know what exothermic means, right? It means it releases heat, releases energy. Why? Why would condensation release energy?
Because it's going to a lower energy state.
Okay. Why?
Because liquid doesn't move around as much, so it doesn't need as much energy.
Maybe,
Like the
right?
molecules aren't.
But, you know, liquids can exist at multiple temperatures, right? Why would you release energy if you go from a gas to a liquid? What changes as we go between a gas and a liquid?
The state,
The state? Well,
temperature.
maybe, right? We'll talk this, so hang on to that thought. That's an interest, so that's something to think about there. That's why I say maybe.
Yeah, like you can have, if you have
Yeah.
something that's super.
Like something with the arrangement of the molecules.
Okay, what do you mean by that?
Cause like they're more spread apart, like in the gas.
Uh-huh.
That's what I was.
Okay, do you wanna build upon that idea then? if gases are more spread apart, what about liquids? They're what?
Liquids are more densely packed.
They're more densely, they're more closely packed, they're more closely together, right? So what? Why would that release energy?
It requires less energy to hold them together because the bonds aren't spread apart.
What
as
bonds?
far.
Intermolecular.
Aha, right? What's up?
So for gases, it takes a certain amount of energy to prevent those intermolecular forces from bringing the molecules together. So
Maybe.
when you release heat, that heat was being used to keep them moving around or excite them.
Sort of. Well, I'll correct that idea, or not correct it, but I'll kind of, let's say I'll polish it here in this stuff, right? So here's the thought. So I've been yammering on here for about 30-ish or so minutes, right, on these different topics, right? Vapor pressure and osmosis and surface tension. What's the idea behind all of those? Intermolecular forces. Got it? So when molecules start to talk to each other, just like on Monday we said that dispersion forces are the weakest. Does it still have some energy component, even if it's a weak intermolecular force? Yes, it does, right? And we talked about dipoles and how they're a little bit stronger, and we talked about hydrogen bonding, they're a little bit stronger, right? And I had that graph up there that kind of showed a relative scale, it's 40 joules for a hydrogen bond, this kind of thing. That's a measure of energy. So when you form a bond, right, here's the important part, right? When you form any bond, whether it's covalent or whether it's intermolecular, right, you're going to release energy when you do that, right? Why? Well, because it's a good thing, right? Electrons are now interacting with something that's positive, right? That's a lower energy state. I forget, somebody had mentioned that, right? But these molecules have to be closer together for that to happen. And what do we know about gases? Well, there's a lot of empty space in between it, right? They're just zipping around. They don't interact with each other, right? But as you start to remove energy by maybe lowering the temperature or whatever it might be, right? These molecules get closer together, they can form these intermolecular forces, and there's a release of energy that happens with that. Got it? So why would condensation be exothermic? Well, because we make these intermolecular forces, we release energy with that. So if condensation is exothermic, what do we know about vaporization? Endothermic, which means what?
Is taking in energy. So
We
like,
have to add energy into it for it to happen,
which
right?
is why sweating cools us down.
Yeah, to turn right. So our bodies release energy to make the water evaporate. Yeah. So why would vaporization be endothermic then?
Because it's taking in energy to bring the molecules to a higher energy state where the intermolecular force is reduced.
Well, you're adding energy to break those intermolecular forces apart, right? So it's just the opposite idea. So that's all it is, right? You guys get the point that I'm making here? So if I ask you a question out of this chapter, you're probably got to look for some kind of answer related to intermolecular forces, right? And think about how that relates to the specific property that's coming out of it. Okay? Of course, we're not covering an exhaustive list of all these different applications of intermolecular forces, right? That's an entire, I guess, materials engineering course, right? Which, unfortunately, we don't have that here, right? Or maybe some of you guys are like, no, that's a good thing, right? That sounds scary. No, but remember, all these different ideas is relating back to the intermolecular force. That's all I really want to get the point across to you guys. Okay? All right. So this is a little bit more about what we talked about in Gen Chem 1 there. Right, we talked about changing states and the energy that's released with this, and the measurement and delta H and all these kind of different terms that come along with it. Now we're going to come back to delta H later on in the semester, and what we're going to learn along the way is some of the friends that delta H has. Right. So delta H is enthalpy, and we'll learn about entropy, and we'll learn about Gibbs free energy, and we'll learn about some of these other measures of energy for a system is what it is. Okay. So enthalpy is just one component of that. Yeah.
So presumably the liquid to solid relationship is similar in that it's endothermic to go from a solid to a liquid and exothermic to go from a liquid to a solid.
Absolutely.
Would the amount of, or enthalpy or whatever, needed to take from a liquid to a solid typically for most molecules be greater than the difference between gas and liquid?
All the way around. It's usually higher energy to go from a liquid to a gas.
Really?
Yeah.
So,
Because if you think about it, it's, you know, how much are you really changing in terms of spacing between a liquid and a solid, right? What you're doing is they're already fairly close together,
yeah.
and kind of if you want to think about it in a solid, all they're doing is ordering themselves in a repeating pattern, right? So there is another
What
component.
about ice? Because ice expands space.
Right, now the question would be why with that, right, which is a very interesting question. But back to your point, there's a bigger difference to moving these molecules completely apart also, right? So typically you'll see things like the vaporization having a higher energy than just the melting, right?
Okay, thank you.
All right, so here's a scary looking equation with a fancy sounding name that you can use to impress people, right? So here's a Clausius-Clapeyron equation.
Do I have to remember the name of it?
Nah, right? But it's just a equation that relates vapor pressure and temperature, right? So on the left-hand side there, P2 and P1. So if I'm asking you guys about, you know, calculating the pressure, the vapor pressure at a specific temperature, right? P2 and P1 are the same thing as your initial and your final temperature, right? So P2 you can think of it as the final pressure, P1 you can think of it as the initial pressure, right? So which are the two changes there, right? Delta H of vaporization, there's an enthalpy component for you guys, right? Which in some cases you might have to calculate that on your own, right? But we know about how to deal with delta H, right?
And then the R is the R gonna be that stupid 8.0206 thing?
Well, R is a constant, right? But it's a little bit different than that one. Yeah. Yeah. Why is a constant stupid? It's like one of the easiest things. It's like, oh, I hate it when it's so simple to remember one thing, right? But R is a constant, right? I'll give it to you guys in just a second here, right? Then T2 and T1 are just the separate temperatures there, right? So nothing too complex, right? There's 1, 2, 3, 4, 5 variables, right? The two pressures, the two temperatures, and then delta H, right? So if I ask you guys to solve an equation with this, right? There's 5 variables, I have to give you what? 4 of them, right? So when you're trying to solve a problem like this, look for those 4 variables and what information you have to fill into there, right? Now, why this is useful is because we can actually start to plot out linear data with this, and we're not going to talk about that too much in this class, but when you get to the upper division chemistry courses, right, making linear graphs to predict properties and gather data out of it is extremely useful, right? So I think for some of you guys who've gone through statistics, right, we always want to try and make linear graphs. Why? Well, they're easy to model, right? We can easily model a line where if you have some kind of polynomial function to predict predict data, it's a little bit more wonky, right? What's up?
I think I know, I just wanna make sure I know. And delta H, the enthalpy, is that how much energy it would take to vaporize?
Yeah.
Something?
Yeah, the energy required to turn something into a gas. Yeah. Now, note here that I tell you explicitly that absolute temperature, which means in Kelvin, needs to be used. But you guys already knew that, right? How did you guys know that this has to be in Kelvin? What's special about Kelvin versus the other temperature units?
Because,
Yep, so when we convert from Celsius to Kelvin, right? What's special about the Kelvin?
No
Because-
negative.
There's no negatives and there's no zero. That's practically achievable, right? So if you'll notice, we have to divide by temperature. What happens when you divide by 0? Right? Syntax error, right? So, whenever you see temperature in here, just make sure you guys are in Kelvin, right? All right. So a little bit of a simple start here to use that equation. See what you guys can come up with. We'll give you guys some info for what you need. Ooh. There it is. So our constant is 8.314 joules. careful.
Hey, Doug.
What? You don't know what you're doing?
No.
What's the question?
Are we treating P and C as like single constants? But I mean, what I mean by that is like, are we doing fractional division of
You get it.
Are we doing, or are we just assuming that? I think I'm just assuming there's that.
One and two. So I'm giving you the,
Yeah.
notice what I asked you, right? Normal boiling point is 100 degrees. So at a specific pressure, what's the normal pressure? What are you feeling in here? That's the question. You got what I mean?
Hold on, I don't know how towards, wait, no.
Didn't I just give that to you in a previous slide? So that's why I said, what's up?
I understand you're gonna go through it, maybe it would help a little. I don't know what are you asking? You're asking for, I see a little bit of guidance, I guess. You're asking for what temperature of boil at.
Mm-hmm.
Usually this, not because of a certain pressure.
Mm-hmm. So the normal boiling point is at 100. What is, what was it? Right, so normally we're at 1 bar, right? And I say, well, we're in torr here, so what do you feel in terms of torr right now? That's the question that's the information that you're missing, right?
What am I feeling?
So 760 is what it is at
Cause it's the millimeters of mercury thing.
Mhm.
Well, how do you convert towards the millimeters of mercury?
Hmm?
It's the same, torr equals
Oh.
millimeters of mercury, yeah.
Oh, yeah, that's right, yeah.
What did you decide quickly?
I think Q1 is gonna be the 760.
Okay.
I think some of you guys are starting to see the little snag there, right? So,
Comparing the 100 to normal and then the 500 to
so at a different pressure, right? We need to figure out what the boiling point is there. But we need to know the pressure that we start out, right? That we start at to have a boiling point of 100 Celsius, right? So that's the missing blank, right? Because remember, there's 5 things you guys need to figure out, right? There's 5 variables in the equation, right? Delta H, and then the 2 pressures and the 2 temperatures, right? Well, I give you the information about delta H. I gave you information about one of the temperatures and one of the pressures, and so then we were missing a bit. And so this is, the reason why I give this problem here is because I don't know if it's still in this edition of the textbook, but this used to be one of the textbook questions. And so I put it in here just because one of the trickier things to pay attention to, I guess, is just when the book gives you information, but it's not explicit about it, right? So what I mean is this, right? What it's really saying is when it says like the normal boiling point is 100 degrees Celsius, right? That's what you guys know, right? You guys know it boils at 100 degrees Celsius, but remember now we should say, well, if it boils at 100 degrees Celsius, then we have a specific pressure that's associated with it, right? It's the pressure that you guys are feeling right now. And so in this room, what would the pressure be in core, right? What's the normal pressure if you want to think about it like that?
760.
And so that's 760 torr, right? Whoops.
273.15.
Got it?
Is that something you would give to us on an exam?
Yeah, I wouldn't be this dumb about it. Like I said, I don't really like the way this question is written, right? Because what'll happen is you might run into that snag and like, well, I don't know what to do, and then we kind of cascade into a wrong answer, right? Yeah, what's up?
I'm still kind of confused on how you got the 760 torr part.
That's just what that's one atmosphere.
Oh, so that's just like the standard?
Yeah.
Okay.
Yeah, there's different measurements for pressure. And if you like do a Google search for, what is 1 atmosphere in millimeters of mercury, right? You'll come up with an answer for that kind of thing. Well, what else? You're given
The kilojoule.
temperature in units of Celsius.
So you gotta add 270.15.
You've got to convert it to Kelvin, right?
And then the stupid, enthalpy is given in kilojoules instead of joules.
Aha.
Bummer.
You guys catch that? Enthalpy is typically reported in kilojoules. But notice your constant is in units of joules. Okay?
Wait, what's the K?
That's
Kelvin. Yeah.
Oh.
Yep.
Yeah, so you just like.
It's only day 2. Don't give me those signs yet.
Come on, Chris, this is.
Alright, so this is, like I said, this is where, Gen Chem 2 can become a little bit nitpicky, right? So really, and for those of you guys who had me for Gen Chem 1, I always kind of poked at you guys to make sure you do what? Write out your units with everything. It's going to be so much more important in this semester. Okay? Now I know some of you guys, you hear me, right? Everyone, voice check in the back. You guys got me? Yeah? Test 1, 2. So some of you guys, so all of you guys hear me when I say make sure you write out your units. And 70% of you guys are going to like, he's talking to somebody else, right? He doesn't mean me. He doesn't know how awesome I am. Well, now I know you guys are awesome, right? But I make mistakes with this stuff too. And do you know how I catch most of my mistakes?
By checking?
By looking at my units, okay? You're like, now some of you guys are like, I'm better at chemistry than he is. You probably are, okay? But you're still gonna make mistakes. Don't make mistakes. I'm just telling you, just get in the habit, write out your units, and you're gonna catch your mistakes that you guys make, okay? That's it, it's as simple as that. Now, for those of you guys who've had me before, I also made you another promise. Because I know that when you write out your units, it costs you guys calories, right?
You'll bring us donuts? You never
It
do.
costs upwards of like 1/10 of a calorie to write your units out. I know, times are tough. Calories are hard to come by, so I will bring you guys donuts if it's a caloric problem, okay? Does that sound fair?
You never brought donuts last semester.
Well, you guys never complained, so I didn't have to buy it.
Read the subtext of the disgruntled glares.
All right, so just get in the habit, write out the units, that kind of stuff, and then we can catch some of these things, okay? All right, so let's all put this together then. So natural log, 500,
Wait,
right?
what? Where did the log come from?
From the formula.
Oh.
Oh, what?
I completely.
Whoa! Okay, let me back up. So step 1 is write down the equation properly. Oh man. You guys got it now?
No? What am I missing?
No, my goodness. Alright. So natural log, we've got, let's see, 3.71 kilojoules per mole, right?
Oh, that was an ln, not an ion.
I don't know what IN would mean.
In?
Oh, that's what you guys thought that was.
Yeah,
Oh,
I thought it said in.
Oh, sorry, no, yeah, I'm sorry, I should have been more explicit about that. Joules, Kelvin, mole. Then 1 over T2 minus 1 over 373.15. Alright, cool.
Day one of
It
the
is.
classes for
Day
me.
one, and we're
I'm
already-
not.
It's all good. So something like this, with the exception of what? What's the mistake that I currently have?
Kilojoules versus joules.
So don't forget to convert this into joules. How do I convert kilojoules into joules?
Divide, just move the decimal thing.
Negative 40.71 kilojoules, right, per mole. I need to convert kilojoules into joules. So how do I do that? Yeah, what's up?
Why do we have to convert into joules, cause of constant?
This is in units of joules,
Lower
right?
I see.
So either convert the constant into kilojoules or convert the other one into joules. Okay. So for every 1 kilojoule, there's 1,000 joules, right? You guys remember how to do that stuff, I hope? Yes?
Oh,
And then if we plug that all together, my answer that I got for T2 was about 361 Kelvin. It's about 88 degrees Celsius. So if we solve that all out. You know, take your natural log, divide, put this stuff out there. And then we'll do the, I guess, third most important thing, right? Step 1, it's a natural log, not in. Step 2, right? Step 2 is, pay attention to your units. And step 3 is ask the question, does my answer make sense? Okay, does my answer make sense? So, in the problem I say, what temperature will water boil at 500 torr? So, right now you guys are about 760. So 500 is what? A lower pressure, right? What happens to the boiling point when you lower the pressure? It should go down, right? There you go.
So that
Is this below 100 degrees Celsius? Yes. So does that make sense then as an answer? Yes. So if you got something like 500 degrees Celsius, go back and check the minus signs and that kind of stuff. Got it? So I promise your answers should make logical sense. Okay? Should make logical sense. Now this is honestly kind of a tricky point too, right? Because sometimes we deal with these complex types of problems there, but in this case we can go back and qualitatively check ourselves. Okay. Good. All right. So I think this is kind of a good pausing point for today. We'll go through on Friday, we'll talk about the last one of these transitions. We'll go through some phase diagram stuff. And then after we're done with all that, we'll work a couple more problems out of this chapter, right? Sound good? All righty. Oh, yeah. All right, I'll see you guys on Friday.